Okay, so I'll just do a, hopefully, do you mind starting the timing? I'll do a very short recap in 2 minutes of what the point I was trying to get across yesterday. And then I'll move into explaining this environment, this thing that's here, because I think this is a non-trivial idea, and it's the main thing I want to get to you in the first half of this lecture. So the idea actually is very simple. Yesterday I told you, a lot of the time when you're doing community ecology, you're a bit in this selection or filtering framework, where basically what you're saying is, I don't really care to go deeply into the population dynamics, into the local volterra. The main thing I need to know is roughly, is the species selected to be there or not? Which is a bit like saying, is R positive or negative, maybe, or is K positive or negative, something along those lines, not going deep into the dynamics. And the two big things that people look at typically are the abiotic environment and the species traits. And so basically, this is a matrix. So my indices here is species composition is abundance of species I at position X in space or in sample X. Tell me, can you see the indices? Okay, perfect. The abiotic environment is going to be value of some factor E alpha at position X. And species trait is going to be for species I, there is trait beta, right? So you have all these matrices that you're trying to relate one to each other. And one way that you could do this is just pure stats, try to somehow find regressions, correlations between all those numbers. But you can go a bit more into the mechanisms of it. So for instance, just as a reminder, for the people who are very confused by the graphs with two axes I was showing before and these kind of things, this axis, these graphs were just trying to say, for instance, if I look at my matrix of species traits, so for now, here I draw a matrix, right? For each species and each possible trait. So species I, J, trait beta, gamma, etc. This is what is the value of that trait. So it could be big size for a bird, color, whatever. The axis I was showing before was trying to say, can I decompose this matrix as, let's say, effectively just something like a rank 2 matrix. So let's say this theta I beta. If I had just one axis, it would be, can I just write it as something like UI V beta or something like this, right? Just for people who care about what's the mathematics underpinning this viewpoint, because we can do interesting mathematics even in this viewpoint without going to population dynamics. There are things for physicists that are interesting. It's how do you take a complicated matrix and somehow decompose it into very simple low rank, we call them. And this would be basically, this is one possible decomposition. I will not go deeper, like typically it would be more generally something like this, where you want to have some kind of decomposition of the matrix. I won't go deeper into that because that's really not what we're doing in this school, but it's just in case you maybe some people will understand a bit better what the axis were about, and maybe some people will understand less now, I don't know. But the point I wanted to say is, if you're not going into this really mathematical approach to the data, what you can always say is, in this viewpoint, I'm just going to look at what are the most important factors. And roughly speaking, as you go to higher spatial scales for the environment and higher taxonomic scales for the species, a few factors become maybe the most important, like temperature becomes very important. It's the most universally important across many positions that you could be, many places you could be in the world. Size is the most universally important across many of the things, many species. And the importance of these factors is more obvious when you go to higher scales. So there's this notion that if you do macroecology, like not the ecology of one test tube, but the ecology of the world, probably temperature and body size are going to be the first two things that you care about to get the broadest patterns at the global scale, right? It's an idea like this. I won't spend longer on this. It was just to kind of hopefully give you a better sense of what I was trying to say before. Now, the crucial point is, as long as we're in this selection framework, all that we're saying is that somehow species composition is caused by these things, but not influencing them, right? There's no notion of feedback, as Priyanka talked about this morning. So feedbacks appear typically. I mean, you could have that the species modify the environment. That's very possible. But usually, since the variables that we like to model the most are species abundances, the first obvious feedbacks are feedbacks between species. And so if you zoom into that blob at the bottom here, if you zoom into it, yeah, this thing is zooming into each blob, right? If you zoom into this blob now, what you're going to have is that NA influences NJ and NJ influences NA. So you cannot do simple statistics in principle, except what I'm trying to say here, and to give you as an intuition, is that it could be that the way that these interactions happen is either that what matters is just how species I is influencing the fitness or the R of species J, and then it's a bit like an environment. It's as if it was an abiotic factor. Just a resource could be just nitrogen, or it could be a prey, right? And both are just something from the outside, kind of. There's this intuition. Or does it really matter into the feedback that the species has on itself? And that's the point I'm going to try to make a bit more precise. So I will go to the two-species Lotka Volterra for the joy of everybody who loves Lotka Volterra, to just say, what do I mean when I say that when you have this double arrow, it could work like just an effect on fitness, or it could work as a contribution to feedback. And hopefully, so really, this is a kind of central idea, so I want to get it right. So help me, if you don't understand, help me get it right. So I'm going to go back to the drawing that you've seen 15 billion times for the logistic. So, which I write with this way of writing. So you have something like this, and you start with R, you end up with K, and this is, so N star, which you can also call K. And this is the feedback, right? And the point I was making yesterday is, even if you're in a multi-species context, this R, your initial growth rate, and the slope are really crucial things. Now, what does it mean in a two-species context? So what it means in details, and that's what I want to get across, is this. I'm going to write the equation just for N1. And after that, I will try to convince you that even if I go to something less, like more complicated than Lotka Volterra with nonlinear functional responses and all these things, it's still the same idea that matters. So, okay, so this is, in general, in time, this is always true in Lotka Volterra. This is the definition of the Lotka Volterra model. Now, sorry, my T, this is not an epsilon, this is a T. We should really put a bit more efforts. Let me know if you cannot read my handwriting, just stop me. Okay, so the point I want to make here, which is a bit crucial, is, so you can imagine two extreme limits in which it's easy to understand. Like in general, there will be complicated dynamics, right, potentially. But there are two limits in which it's easy to understand what's happening. First limit is, imagine that somehow I'm keeping N2 constants, right? I have, let's say the dynamics of species 2 are very slow. Maybe species 2 is a tree that lives for thousands of years. So if N2 is constant, what you can see is, in fact, I could say this is just something like R1 minus A12 N2, which is now constant. I'm going to say K2, in fact, because it's at current capacity, let's say, minus A11 N1. So what the species 2 has done is it has moved my effective growth rate. Instead of being at R1, now it has, let's say, decreased if it's competition to R1 minus A12 K2. Okay, so I invade less easily when there's a competitor. Okay, and if this is all that's happening, if species 2 is really kept constant, the slope here is going to be the same. So instead of, this is what the equilibrium I would have if I were alone, with slope minus A11. And the equilibrium I have if I'm not alone, but the other one is not moving, is just this other thing here, which I start from a lower k, but I have the same slope. So a situation that would look like this is a situation where I would say the other species has changed my fitness, but not my feedback, right? The slope here is the same. Actually, that's not very obvious. Yeah, it's kind of obvious. The slope is kind of the same. The only thing that has changed is this kind of, am I able to invade? How much will I grow? And you can see that this has consequences for the eventual abundance I reach, right? But now I can do another limit, which is easy. Imagine that I replace N2, like that. Now, so this was the situation. This is the situation in which N2 is very slow, infinitely slow. So not moving, constant even. Imagine the other limits where N2 is infinitely fast. Now, the other species, let's say it's a virus, and so at any given point, its abundance will adapt to me. So in fact, now what I have instead is, I'll try to write a bit more horizontally too, is minus A11 N1 of t minus A12 N2 star of N, at a given N1, right? In a sense, what I'm saying is that at any given value of N1, N2, the virus will reach some abundance very quickly, its own equilibrium, and then it changes as N1 changes. And what you can do is you can actually compute what this gives. And what this gives is that as a slope here, so instead of minus A11, so it's nice because, again, this becomes just a function of N1, right? We're back to being able to draw this graph, because when you have N1 and N2, you don't have a single line here, right? It would depend on the value of N2, where you are in this graph. But if N2 is either very slow or very fast, you can just go back to N1 alone, and you get what's happening. And what's happening, in fact, and that's the whole game, is that, so this is still true, right? Whether when I arrive in a system where species 2 was at K2, this is my initial growth rate, my fitness. But now the slope here is going to be minus A11 and yes, minus A12, A21 over A22. You can compute it, it's not very hard. And so this is the thing I have, in fact, hope just after here. So the problem is here, I did it for predator-prey, so it's not the same science. You'll have to trust me, I guess. Ah, this is a bit annoying. Sorry. Well, okay. I'll leave it as an exercise to show that. If you're in the predator-prey case, instead, it looks like this. The intuition, what this means is very simple, in fact. What this means is,
who's predator and who's prey?
Here, I'm doing prey is 1 and predator is 2. And what this means is that now the signs, I have a minus here and I have a plus here. So it just changes the signs, but it's the same equation, right? So I'm just going to ignore this. I'm just going to stay on this picture. And so what does this mean intuitively, right? This is A11 is the immediate feedback I have on myself directly. And A12, A21 over A22 is the feedback I have through the other species. So what's happening is, if you imagine there is species 1 here, species 2 here, I have my immediate A11, that's how much I limit myself. And then there's this thing going through N2, and the expression of that is this A12, A21 over A22. That's going to be the intensity of this feedback here. So the thing that you see, for instance, in competition, one thing that it does is I'm self-limiting, I'm killing N2, and N2 is killing me, which means that as I'm killing N2, I'm having a positive feedback on myself, right? If I'm killing my competitors, I'm making the world better for myself. So in fact, in the competition situation, the feedback through the other is a positive feedback. And so now what's going to happen, the density dependence is going to be the combination of this negative feedback I have directly on myself and positive feedback I have on myself through the competitor. Which means that, for instance, if this positive feedback was to become very large, if I have a very big impact on my competitor, I could in fact have something like an LE effect, where the positive feedback is even stronger. And so somehow I can, like just from killing my competitor, I make the world better and better for myself, and I grow faster and faster. Yes?
You take the slope.
Yes.
What, like N2 becomes a constant, and then what do you write? Like there's a bracket of N1 there.
So if N2 is a constant, then you see that N2 here just becomes K2. So it's just a change of R, right? So it's a bit what I'm saying, that in the very short term, before feedbacks become important, the other species just acts like a change of your basic growth rate.
And what about that case where you have an N2 star and...
Right. So in this case, what you would do is, here, the way that you would get this is try to solve the N2 over dt equals 0. for a given value of n1. So it's saying that you have those two dynamical equations, but one gets to 0 much faster than the other. It equilibrates much faster. So at any given instant, I can replace n2 by its equilibrium value. It's like a bit of we can call them a slave variable. Maybe you've heard this term. It's a variable that just is tracking whichever value is allowed by the other one, right? So which means that n2 star just becomes now a function of n1. That's all. I can leave it to you as an exercise because I want to go a bit further. But it's important that you get roughly this idea. So what would happen? So the curve here, that's the solid curve, is the thing that you will actually see in the competitive case if n2 is very slow, n2 is very fast, sorry. And if n2 was very slow, what would happen is you would start on this curve. I don't see it, but this is not really an equilibrium. Eventually, n2 will start to change. So you would start along this curve and then slowly converge towards the real equilibrium. Because the real equilibrium does not depend on who is fast and who is slow, right? No matter how fast or slow you are, you will reach the same fixed point if there is a fixed point.
What is the K2 there?
What's the what, sorry?
The second equation K2, A12 and K2. So in the second equation, you have a K2.
Here?
Yeah.
Yeah. So all I'm saying is I replaced n2 by n2 star, which is some kind of fixed value of n2. Actually, n2 star is a bad idea because, well, I guess, yeah, by n2 of t0, let's say. That's how I should write it, actually. I'm just saying that from the perspective of n2, we're still at initial time, like it's not started changing yet. So we just keep the initial value of n2 here. And so you see that if this is not a changing variable, then this is just a change of r. Okay. Does anyone feel that this is not clear? I mean, feel free to raise your hands, even if you don't know how I could clarify. So who would like more clarification of this? I think it's okay. Kind of. Okay, so maybe you'll see a bit more of these things later.
Just a small
sure.
So why is it still a straight line in the second case when it is fast?
So if it's very fast, it's a straight line because, in fact, you can check. It's easy to check that this is a linear function.
Because you're assuming the next.
Because at equilibrium, this is a linear function.
Right.
And in fact, that's a general property of Lotka-Volterra that everything is linear unless you have a species extinction. That's the only way that you get some nonlinearity, like in terms of the equilibrium, right? The equilibrium is just a linear, combination. Yeah. So now what I really want to say is that a species, as you can see from these two expressions here. So this is this expression for the effective effective slope minus a tilde. And this is the expression for the effective, I'm going to put ones here. And I'm going to write this larger. So what this is saying here is that it's very possible that, in both cases, the interaction between species 1 and 2 is important. But it's very possible that, for instance, a species contributes very little, that this term is small. So R1 tilde is almost R1, but that term is big. So the species does not matter very much as a fitness changer, but it matters a lot as a feedback changer. It could be that the species matters a lot as a feedback as a fitness changer, but not at all as a feedback changer. Right? If the direct self-regulation A11 is very large compared to this other thing, then we can completely forget the contribution of the other species to the feedback. And that means that for whichever species this is approximately just A11, then that species is just acting as an environment. That's the condition under which you could say, yeah.
Can you help me to put it in context? It's well known that if you take consumer resource model, especially if the resources are themselves biotic, exponentially growing entities, then you can sort of, if the resource dynamics is fast, then you can integrate them out and effectively have the competition within resources.
Absolutely.
So what I'm trying to see is that your expression here would have the wrong sign for this. Is it because this is a sort of predator prey situation? Because the bottom line is you can have for micro, for instance, consumer resources.
Yeah. No.
A11 will be actually zero. There is no self-limiting factor, but it emerges through competition via research, via this second term A1 divided by A2.
So what would appear here, in fact, is this is just one. So if you don't have A11 at all, what's going to happen is indeed, if you just take a look at the two competitors, you have only positive feedbacks in this situation, which is very simple. It's just telling you that I will grow and grow and grow until I kill my competitor. This is exactly the same thing telling you that, okay, if I...
Just the carrying capacity essentially will emerge because of the...
Not really. So I mean, so if, okay, let me write it this way. If you have N1 and N2, sorry, N2, and they're eating resources, or whatever.
Maybe just one resource.
R1, okay, let's do this. Then what's going to happen is how much they eat R1, there will be a 1-1 here. This is going to be, Aij is going to be consumption I alpha, consumption J alpha, right?
Yeah, exactly.
So there is an A11, there is A12, and in fact, if you plug this into this, you get something that's very interesting. It's that actually this is exactly zero, identically zero, because this is going to be C1, C2 minus C1, C2, C2, C1 over C2, C2. Sorry, C1, C1. So yeah, this is going to be C1, C1. Let's say there's just one resource, right?
Yeah.
This is going to be C1, sorry, C1, C2, C2, C1 over C2, C2. And what this is telling you is precisely that if I were to draw this graph now, I'm going to just remove, is it okay if I just erase this part? Thank you. So now hopefully you understand why I use slides usually, because it's a bit of a mess, this whiteboard, but okay. What you will have in that case is in fact that if I actually write the N1 star over N2, over N1, starting from some initial growth rate, you have a flat line, there's no feedback, until the point where I reach the abundance at which I kill the other. And then I'm actually just alone, and this is just because it becomes my A11.
Okay, no, maybe I understand where I got confused. I wanted to have the 1 to be a consumer, 2 to be a resource.
Yeah, but then you have just...
And then
yeah.
A11 essentially is absent, but it emerges through the...
Absolutely. So actually this is this case.
Yes.
So here 2 is the predator, 1 is the resource.
Yes.
And indeed you have a different sign. So even if you have no A22, you have a negative feedback just from eating the resource. Right, perfectly. So...
And then you eventually recover just, one of the logistic growths for the consumer.
Exactly.
If the resource can be integrated, right?
Exactly. Okay. So why did I put you through this ordeal for 20 minutes now? It's that I really want to emphasize this notion that if you look now at this, in fact, yes, adding a prey, let's say, would change your growth for a predator prey or consumer resource situation. If you're alone as a consumer, you just die. If you have a prey now, you don't die, you can grow. But then your feedback will be given through the feedback through prey, especially if you can integrate out the prey, if the prey dynamics is very fast. And also your own, if you want. And okay. So the idea here is figuring out, so anytime you have a situation like this, where another species just contributes as a fitness changer, then in fact, as a statistical ecologist, you're happy. You can do statistics. It's as if it was an external factor. So you don't have to write a dynamical model anymore. You're back to purely, in a sense, a selection idea. Am I able to grow? Am I unable to grow? Anytime a species contributes as a feedback, now you get into a bit of a different world. And just asking this question for every species in your system explains a lot about the patterns I was telling you before of biomass pyramids, cycles, and all these things. And so that's now the game I'm going to play. How does this perspective allow you to better understand the pyramids, the cycles, and all these things? Okay. So the game I'm going to play is that you could ask this question for both species, right? There's this strange thing that maybe you get this intuition already, that I wrote this for one species, but I could write it for the other species, which means that you could have a situation in which, for instance, each species is just an environment for the other. The predator is an environment for the prey, and the prey is an environment for the predator. It's a bit strange, but it could happen if somehow the self-regulation here is big for both of them, and so is more important than the feedback through the other. That's the game I'm going to play. So you remember this question about the otters and the urchins, and I think it's one of the basic questions that you ask when you're doing dynamical systems is which variable is in control of the dynamics, right? Who is so in this question I was asking, in a sense, is it the otters who are deciding when the urchins die, or the urchins who are deciding where the otters live, right? And that the first one would give you a negative correlation between the two, second one positive correlation between the two. The problem with this question is, if you get a bit deeper into the things, there are multiple notions of control. And okay, this is the part where I hope I get the message across, because it's a bit tricky. So the trick is the following. When I'm asking if the otters are deciding when and where the urchins die, this could have two different meanings. One meaning that is, maybe I'll do it on the whiteboard first, actually. Let me try to do this on the whiteboard to go a bit slower. And so I'm going to assume that I can erase at least this much. So you got the point across. Yeah.
If I understand correctly about this one being the environment, the other thing that you were saying is,
yeah,
at least for the case where you had N2 being passed, for instance,
yes,
you would have two choices in life. One if N1 is passed, and one if N2 is passed, right? And so based on which of these perspectives, I mean, which is true, then you.
Sorry, no, that's not this. I'm sorry. I created a confusion maybe with this fast or slow thing. The fast and slow thing doesn't change the equilibrium, in fact, right, at the fixed point. So what I want to say is that for every species, so if I write, let's say, R1 tilde equals R1 minus A12 K2, R2 tilde equals R2 minus A21 K1, and now A11 tilde equals A11 blah, blah, blah. And the same in symmetric. I could say for each of those cases, it could be that, so if this is big and this is big compared to R, then it would mean that species 2 has a big impact on fitness of species 1. Species 1 has a big impact on fitness of species 2. This could be true or not, right? It depends on those numbers. In both cases, independently of that, it could be true or not that this number is big compared to this one, which would say that species 2 has a big role on the feedbacks of species 1, and species 1 might have a big role on the feedbacks of species 2, right?
Yes.
So in fact, okay, for two species, it's now the same number here. So you cannot really separate the two. But yeah, actually, no, you're comparing them to. No, it is the same number, sorry. It is exactly the same number. So in fact, for two species, either the feedback matters or it doesn't, right? For both species. But it is very possible that, for instance, the feedback could matter, and the species could also matter as a fitness changer, or it could not matter as a fitness changer. Both are possible, right? Okay.
So your game is comparing this plus and minus terms in all four.
Exactly. Exactly. That's my game, and that's two ways of asking if the species is important or not. That's the thing I want to end with.
Great,
is the species important here? Is the species important here? Right? So
from data,
yeah.
Is there a way that you could just figure out from the data, from what you observe in those pictures there, which of these two situations obtain?
Yeah. So typically, getting the second one without time series is hard. You would have only indirect proof, but I'm going to show you where you would find it in data. Okay,
the argument of one species varying quick faster than the other?
So this idea of quick and fast was just a way to explain how you could go back to just this single graph, because in general, this number here doesn't mean anything in itself, right? I mean, it's a kind of abstraction. It's something that predicts the equilibrium, but if you were to look at data, so you could look at data of growth rate versus abundance in time series. If the time series are not very well separated in time scale, there's no reason to just see a line here. You could see, because your growth rate depends on two variables now, so it could have multiple values for the same value of n1. So this fast and slow idea was just to say under which conditions do you have here a single value on the y-axis for a given value on the x-axis. That was just kind of mathematical trick to be able to write this as a real function. Okay. Thanks for the questions. So to help you understand now what this means for the actual patterns that you see in the world, I want now to do a slightly different thing. The thing that I'm going to do, it's almost the same, but it's a bit tricky. It's that if you think about this thing here, this very same plot, in fact, you can also think of 1 over A is dn star over dr. 1 over A, it's easy to solve, right? If you compute r n star, you would check that this is r over A, which means that 1 over A is how much the equilibrium abundance of that species will change if you change its fitness, right? And so you have this interesting thing that's maybe you notice in the logistic growth that in the dynamics, so in the short term, let's say, I'm going to write it this way, sorry. I'm going to do something short term and long term, and then you'll understand what I mean. Let's say that I write, in general, I want to write dn, oh, I'm going to write it like this, n dot over n equals g of n, right, some function. What I'm saying now is, in the short term, I have that A is equal to dg over dn, right, because g is equal to r minus an. And in long term, I have that 1 over A is dn star over dg. Okay, what does that mean? What this means is, when I write a model like this, and I assume the shape of this equation, I'm saying, as a theoretician, I'm assuming how, at a given instance, your growth rate depends on your abundance, right? So that's this kind of short-term thing. I choose A. I choose this form here, and I'm saying that how G depends on N is just true actually minus A, sorry. Now, if I want to ask the other question, which is, if I were to change the fitness of a species, how would it impact in the long term the abundance of that species? And that's exactly the inverse of that gives me that answer, right? Simply because in the long term, this is going to be 0, right? So I will just have that's n star equals r over A. And so those are two different questions. How does the dynamical process depend on the instantaneous stock? How does the flux depend on the stock? And if you were to change the flux by a constant, how would it change the stock eventually, right? A dynamical model is a relationship between stocks and fluxes. And so you have those two ways that one stock can control the flux. And I mean, the flux depends on stocks and the stock depend on flux in the long term, right? Instantaneously, a flux depends on stocks. And in the long term, the stocks depend on fluxes. Maybe for, yeah.
The second equation, instead of over dn star over d, should be dn star over dr.
So yeah, the idea is that if what I mean by this is, I can define this as what would be n star. Okay, how can I write this? If I were to change g to g plus delta g, I would have n star goes to n star plus delta n star, where this I have just made a constant change in my G forever, right? This is a constant. And I'm just saying that 1 over A is going to be the ratio of these differences, right? It's going to be delta n star. It's not a trivial concept, right? It's a bit hard to understand what I mean by this, but indeed, it turns out that here, changing G by constant is the same as changing R by constant. So intuitively, we interpret it in terms of fitness and whatnot. But if you really think in terms of dynamical systems in general, oh, this looks like a G, sorry. If you really think in terms of dynamical systems in general, whenever you're writing a dynamical system, okay, now I need to probably erase this.
Yeah, but I still don't understand what do you mean by changing G. G is a function of n, right? You have the expression R minus IN. R is a parameter, so I can ask what is the derivative of the fixed point over R. G is dynamical variable, so in your first expression, you were getting A as just, as my n increases, I see how, for instance, growth rate decreases, and that's why the rate of this changes by definition minus.
Absolutely. If you want to interpret this as, what I mean is if I just add a constant to that, it's just changing a function, right? I have G is a function of n, but I can just say that I changed this function to be a new function to which I have added a constant, right? That's what I mean by delta G.
But practically, it means that you change the parameters of your system and you observe
yes.
how the fixed point is changed.
Absolutely. In practice, that's what it means, and that's probably the more interpretable biologically. It's if I was to, let's say, increase mortality of my species by harvesting it, how would it change the stock of the species I have at equilibrium, right? But in fact, I feel that the symmetry of this helps understand something about the short-term versus long-term.
The symmetry is also obscured by the fact that in one case it's minus sign and in another case it's a plus sign.
Okay, fair enough. But I mean, okay, you do have a sense, I guess, that the point I want to make here is the point I want to make here is the two ways that the species could be important for another are also could be interpreted in terms of, is the abundance of a species very influential on my dynamics, or is the dynamics of the species very influential on my abundance, right? And that's the really, really tricky thing that I want to get across. That's for ecologists, by the way, there are some biologists in the room, thankfully. You can think of it in terms of pattern and process, or maybe stock and flux. When you write a dynamical model, you're saying, so this is, let's say, N, and this is G. When you write a model, you're saying, I assume how the process depends on the pattern. I'm assuming how the flux depends on the stock. That's my assumption. That's what I'm bringing to the world. Now, what emerges from the model is the other arrow. So this is assumed. And this is what you get out of this is the result of the model. Right? I don't know if that makes sense to you, but at least for me, it makes sense. So when you build a model, you're assuming how the process depends on the pattern. And as a result, it will tell you how in the long term, the pattern will depend on the process or the stock on the flux. And so if I go back to my otters and my urchins, that's what I wanted to get across. When I say that the otter is important for the urchin, am I saying that the dynamics of the otter are going to control the abundance of the urchin, or the abundance of the otters is going to control the dynamics of the urchin? And that's not the same answer necessarily. One could be true, the other one could be false for the same set of parameters. And somehow that's what explains all the mess that comes later. So one way of interpreting it is, if you give me an otter population of size n, does it eat many urchins? So is it changing the dynamics of the urchin a lot? Or if I let the otter population grow, if I let its dynamics happen, will that dynamics be the one fixing the population of urchins? Is the dynamics of otter controlling the population of urchins? Okay, now I'm going to try to give you another way to interpret to understand these points. So this is actually what I was writing here for a logistic. If you go to a many species case, what you will actually realize is you can ask the same question in the short term. How do the dynamics depend on the abundances? That's the Jacobian matrix. That's exactly what we mean by the Jacobian matrix. It's how do the dynamics depend on the variables. But in the long term, is the equilibrium abundance of I very influenced by the dynamics of someone else? That corresponds to the inverse matrix. And so that's exactly the intuition I'm building towards, that is going to be true still for many species, and it's going to be true for more nonlinear models. It would be a more general notion of inverse, but that's the core of what's happening in here. So the properties of A are not necessarily trivially related to the properties of inverse of A. For a single number, it's trivial, right? A is just I mean, if this is big, this is small, and whatnot. For inverses, for matrices, it becomes much more interesting.
Is there also a sign difference in the one and two?
Yeah, probably. You probably want to put a minus here. Or, yes, absolutely. And so this is where I arrived to something that really puzzled me when I was starting to look at these very simple food chain models. I was like, how are there still discussions about food chain patterns? Those are very simple models, right? We should be able to understand what's happening. And the point is that, so I'm writing a very general version of what Priyanka was talking about this morning. But there are kind of two traditions in which theoreticians have been thinking about, let's say, the biomass pyramids or the dynamical responses of those species. One tradition is to say, I completely ignore the self-regulation, right? The AII, which here is D. I'm sorry for the notation changes. I've coupled this from various sources. If I completely ignore the AII, you see that there's something very intriguing happening, which is that the equilibrium of B2 is controlled by the dynamics of B1. It's in the equation for B1 that you fix the equilibrium for B2. And the equilibrium for B1 is fixed by the equation for B2. So somehow it's a case where the equilibrium of each species is controlled by the dynamics of the other species. What that means intuitively is, for instance, the resource will grow until it fixes, it has so many predators that it cannot grow anymore. And the predator will grow until it fixes the resource, right? Each species dynamics is fixing the abundance of the other, which is very different from this intuition. If self-regulation is very strong and you can ignore the other terms, whatever. I mean, you could go more, I don't want to go into all the details, but if self-regulation is very strong, if A11 or D1 is very large, what you have is simply that the equilibrium of each species is fixed by its own traits, right? It's the growth of species 1 that fixes abundance of species 1. It's the growth of species 2 and attack rates and whatnot that fixes the abundance of species 2. This is meaningful not only mathematically, but also biologically, because what a species can evolve is its own traits, right? A species cannot control the, let's say, the mortality of predator cannot be controlled by the evolution of the prey. So here, if you're in this situation, if the prey evolves, it will change only the abundance of the predator. The prey has no way to evolve in a way that will change its own abundance, right? It has no control on itself, in a sense. It's the traits of the other species that control your abundance, right? Let's say here B1 is going to be mortality of the predator divided by attack rate of the predator. So those are the two extreme cases in which many people have thought, if you want to really think of this easy notion of, you know, I put food into a system and some fraction is converted into the level above, and that fraction is converted to the level above, you have to be in this picture here. That's the picture in which if there is more food, there's going to be more predators. And if there's more predators, there's going to be more predators of predators. And that's obvious. In this picture here, if you add more food, it only creates more predators. It doesn't change the amount of prey that you have. Okay? So if this is reasonably clear, I think from there on, it's smoother sailing. So, yeah, sorry. The point is, imagine that, okay, I'm a farmer. So I have plants and I have herbivores that are ravaging my crops. You know, it's a big problem. So I'm like, I want to have more food, more plants. I'm just going to put more nitrogen. So I'm going to increase the growth of the plants. And therefore I will have more plants. If you're in this picture of the world, this is true. More nitrogen will increase the biomass. Maybe the biomass will also increase a bit the biomass of the consumer, but who cares? This biomass here is just fixed by G1 over D1, right? And G1 is what I'm increasing. In this equation here, if I put more nitrogen, it doesn't change the biomass of the plant at all, because the biomass of the plant is just controlled by the equation of the predator. It will just make more predator. I put lots of nitrogen and suddenly I have insects everywhere, but the same amount of plants. And now you can understand, like the R-star rule happens in a world like this, right? In a world in which the amount of resource is completely controlled by the dynamics of the predator. Right? This is the R-star, in instance, the biomass fixed only by the equation of the predator. But as soon as you put some self-regulation on the predator, this is not necessarily true anymore, right? So this is why, so far, every time we were writing a consumer resource equation, we were always removing the self-regulation of the consumer, being like, okay, I can do that. It's not going to endanger my results. In fact, it's a very strong assumption, because it pushes you necessarily into a world in which the dynamics of the predator will completely control the amount of resource that you have. Yeah.
Could you give a sort of a practical example of what self-regulation of a predator may mean? I'm trying to map it onto my kind of intuitive understanding of bacteria and phage systems.
Yes.
And phages don't have this second-order self-regulation. And that means that they are always in this mutual control setup on the right, which I assume to be the only thing possible. But maybe in more macroscopic predator-prey systems, you can have the...
Actually, what I want to say is more something, I don't have the figure here, sorry. Imagine that, okay, in the world, I'm modeling here, in my model, I have put, let's say, lion and zebra. It seems intuitive that there would be feedback through this, right? Now, the question is, the self-regulation of the lion could come from, it comes from anything that is outside of the model that can act as self-regulation. So there is very concrete examples. For lions, lions fight for territory, so they kill each other. This is direct self-regulation, right? They kill the babies of each other, infanticide, siblicide, they're horrible, huh? Very bad animals. Many animals actually do that. There are many sources of mortality or lesser growth that you get directly. Self-toxicity, many things are toxic to themselves. It could also be that, in fact, there are viruses here, right? And since this dynamics is much faster than this one, effectively, it is as if this dynamics I'm not modeling is a kind of self-regulation.
So it needs to be a negative self-regulation.
Yes, absolutely. Absolutely.
In other words, if the growth rate of the lions is not just constant, but something which increases with the conservation of lions, then you may actually end up in a situation where lions and zebras are independently controlled, and this
exactly. Exactly. You could have something where the zebra itself has its own viruses or its own fighting for territory. And then
zebras have carrying capacity because of the grass.
But no, but you could ask, okay, but why should the grass itself be self-regulated? Why would it be trivial that any level we should have this logistic term? In fact, it's never trivial for anyone that this logistic term should be there. This logistic term is always something coming from outside your model, right? And so in fact, it's exactly like friction in physics, right? Friction is a bunch of different things happening. So most of the time we just say phenomenologically, friction is this much. For self-regulation, it's the same, right? It's the same intuition. Most of the time, you have no idea how many other mechanisms are outside of your model and causing this thing here.
No, I'm with you. It's just that it's easier to imagine if something grows on its own, well, by eating grass, of course, but if you model zebras as something which has a naturally positive growth rate, and lions are decreasing this growth rate, then everybody will understand that if there were no lions, zebras will not grow indefinitely, they will eventually saturate. And that is this negative self-regulation. Whereas for lions, they will not grow on their own without zebras. So their natural growth rate is negative.
Sure.
And what you are saying is that if I just do the sort of quadratic effect, that they are not just proportional to their abundance, but also proportional with the second term proportional to the square of their abundance, then you may actually end up in a situation where they control themselves.
Yeah. Yeah, and I mean, it's not if you start to include, plants like a grass in your model and the nitrogen, there's no reason why at any level, that level should be the one that's obviously self-regulated and that gives stability to the rest, right? There's nothing obvious about this. In fact, some models of food chains assume there is zero self-regulation at the bottom and all the self-regulation is at the top, right? You could do that. Why not? put all the self-regulation on the lions. There are good reasons for that. By the way, as you go to higher and higher organisms, more and more of their activity is being spent on, let's say, sexual selection. When two lions fight each other when two males fight each other for a female, this is not helping their growth. This is not helping their feeding. They're spending lots of energy on that. And you have many, many sources of this self-regulation. That's actually a point I wanted to make later, but if I'm making it here, it's very fine.
Matthieu, sort of connecting to the lecture in the morning about the MacArthur-Rosenzweig model.
Yes.
Where there were two components. One was a self-regulation component of the resource,
yeah,
and the other was a consumption by the consumer.
Absolutely.
And when you look at the per capita growth rate change, the resource with increasing resource concentrations, you initially saw below critical resource where there was an increase in the per capita rate of resource,
sure,
where the consumer controlled what that per capita rate was. But then as you increase the resource concentration, the self-regulation aspect sort of came in and sort of dropped that curve down.
Sure.
And so I'm thinking like this sort of dichotomy that you presented is something that sort of brought together again in certain types of.
So it's a bit different here because so in that model, I mean, okay, one thing it is saying which is true. One way in which you're saying something which is which feeds into the story here, I feel, is, for instance, it could very well be that you have an initial positive effect, and then because of the consumers, it ends up being an overall negative effect in the longer run, right? Here in Lotka-Volterra, you have only a line, but it could be, if you have more nonlinearity, it could be not a line, right? It could be something like what Priyanka drew this morning. Now, in that model, Priyanka was still assuming that the consumer has no self-regulation. So in fact, it remains true, even in her model, that the consumer completely determines the abundance of the resource, right? So in a sense, there is full control of the equilibrium of resource by dynamics of the consumer, even in her case. So it's not completely, it's not exploring all the possibilities of this dichotomy, right? Where in fact, there are 4 possibilities, right, in this dichotomy. It's not like just, is the prey controlling the predator or the predator controlling the prey, which was suggested by this idea of, is the urchin controlling the otter or the otter controlling the urchin? In fact, you have all 4 possibilities that each species could be controlled by itself or the other, right? And so I can tell you that the way that you would generalize this idea beyond Lotka-Volterra to more nonlinear models is just this V here is just going to be precisely this term here. In any model, you can ask how much the equilibrium abundance is going to depend on, let's say, its own growth rate. That's something that you can compute even for a much more nonlinear model. And that is going to be what matters in general for this picture beyond Lotka-Volterra or for many species. You can generalize all this for many species. It works pretty well.
What about the signs in number 4?
Yeah.
Should be absolute value or?
Yes, it should be absolute values. Yes, because the signs are going to so you're right. This is all absolute value, sorry.
But you can have this unusual situation in which somehow they almost cancel each other. One is positive, one is negative, and effective A tilde would be close to 0.
Yeah,
would
so
it be something to consider?
So this is exactly the thing I was showing when you have 2 consumers on a single resource. What this means is that if this feedback is effectively 0, it tells you that how much worse I'm making the world for myself is exactly compensated by how much I'm making it through killing the other. And so it's saying I'm on the kind of surface, kind of neutral. It's a generalization of neutrality, in fact. Having the most obvious way of having this being 0 is if all Aij equals A, then trivially A tilde equals 0, right? Mm-hmm. If everybody interacts in the same way, you always have that this feedback is 0, which means simply that in neutrality, you can replace one species by another completely neutrally. And if they have a difference in fitness, now the more fit will just win, always, right? So when A tilde is 0, the only way to get coexistence is to have exactly identical fitness. So this again relates to what Priyanka was saying this morning, right? That's 2 ways of getting coexistence is either your fitness is exactly the same, or you have overall negative feedbacks that allow you to coexist even though you have different fitnesses. Okay, I just wanted to say one thing about the mutual control, one more thing about this mutual control situation where somehow the predator controls the prey and the prey controls the predator. Intuitively, this is the only scenario in which you could have cycles. Why? Because what is a cycle? It's saying that there is a moment where the predator is going to influence the prey a lot. So the prey will really crash. Then as the prey is going back up, it will influence the predator a lot. So each species is strongly influenced by the dynamics of the other species, right? So it could very well be that in other of these 4 scenarios, the predator still has a big impact on the prey, just as an environment. Like if you remove the predator, it will change the prey abundance a lot, but you would not get cycles. You would get this kind of cascading effect of plus, minus, but you will not get cycles, okay? So in a sense, here is a situation where the plus, minus that I was showing yesterday is important. This is a situation where the plus is important, and this is a situation where you would expect cycles. And this is a situation where you get this intuitive biomass pyramids of conversion from one level to the other. I can put all these, I'm going to do that right at the end, put all these patterns in this graph. Now, this mutual control situation where each controls the other, it has lots of counterintuitive properties. And one of them, for instance, I will just give you an example, is in this mutual control situation, by the way, those words are mine. They're not very well established in the literature. So don't Google them, you will find nothing. But I mean, I think they're intuitive, right? Mutual control is each one controls the other. It's not mutualism at all. So sorry for that, maybe that ambiguity. But everyone's dynamics control the other abundance. In a situation, if you were to ask, I do an evolutionary problem, an eco-evo problem now. I look at my predator, it's increasing its growth rate, eating more and more. If you look at the abundance as a function of the attack rate, of the predator, at first, the attack rate will increase as long as you're not in mutual control. And once you are in mutual control, when the feedback through the prey becomes important, in fact, the better you are at eating the resource, the lower your abundance. It becomes worse and worse for you to be a better eater. So basically, I would claim, being like putting my big shoes and making no subtlety, having no subtlety whatsoever. I would claim that every time there is a bit of a counterintuitive eco-evo result where, oh, that's strange, I'm evolving towards something that's killing me, or something, not every time, but oftentimes, let's say, oftentimes it would be a situation like this that creates those counterintuitive things, where you're going towards things that are bad for you, or where, for some weird reason, it's the trait of another species that is very important for what you do, or this kind of things. Okay, I think in the interest of time, I'm going to roughly skip this. I'm just going to say that, yeah, I'm just going to skip. Okay, I'm just going to show this, right? That at the end of the day, if you're asking, if I look at my pyramid of stocks, right? I just look at the stocks, at the biomasses, and I want to say, is this explained by bottom-up effects or top-down effects? Like, is it really due to the predator that it looks like this, or due to the plant? In fact, it's not a yes or no question, because there are 3 different places where the predator and the prey, where bottom-up and top-down effects could matter. No, actually, this is probably, no, I would need to go through the details of that. So you'll look at the slides at later times, and you'll tell me if you understand this. Okay, I want just to summarize, to say that, what we wanted to explain in this kind of ecology was, okay, I have pyramids, I have these cascading effects of plus, minus, I have these correlations between different species. The way to explain them for me is really, for each of the species, you ask, is the other species environmental feedback? You combine this for the 2 species to ask, for instance, is each part of a feedback for the other? And then you could have cycles. And then the static pattern is just a combination of those effects, of all those effects, in a way that's are not very complicated once you get everything else. Cool. So here are some conclusions for this lecture, which, if you remember, included also the whole part that I erased. I think what I'm going to do is I kind of want to get started a little bit on the first third of the second lecture. So I'm just going to take 1 minute break. You can look at those conclusions. You can think about questions if you're weirded out by things I said. I'm going to drink some water, and then we can go to the second part, if that's okay for you. Or even, I mean, you don't have a choice. Yes? Okay, I think I really shot myself in the foot with this timescale idea. So, okay, there's an interesting point here. You you can have a situation of mutual control in the sense that feedbacks through the other species are very important for the two species at equilibrium. Equilibrium is at infinite time, so timescales do not matter anymore, right? Now, to have cycles, it is true that the timescales should be comparable, right? But you could have other weird equilibrium properties of mutual control, even if timescales are not comparable, right? For instance, this result here, that in mutual control, a consumer who eats more has lower abundance, typically remains true no matter what is the relative speed of predator and prey dynamics, since it's an equilibrium property. Yes?
So, in fact, it should control
So it is a necessary, not sufficient, as we've established, but necessary condition, I think, to say cycle.
So the original not covered, right?
Ah, yes, okay. The original Volterra is a weird thing. It's neutral cycles. That's the thing I have not smoked out. Actually, I don't know if there is a way to reframe the neutral cycles, so there are a special case of this or not. So I don't have the answer. I know this is kind of true. I mean, I have good arguments mathematically, basic ones, but good, I hope, for why this should be true for limit cycles.
I have a follow-up to exactly this question. Again, I'm mapping onto one system, predator-prey system, which I know well, bacteria and phages.
Yeah.
Bacteria have the, in standard way of modeling it, bacteria have the negative A11 in the sense that they have the carrying capacity even without phages, whereas phages don't have the A22. So by your calculation, since what matters is the product of A11, A22, A11, A22 is simply zero, as long as one of them is zero. And that is clearly the situation where this mutual control is important. And that I understand, except that the cycles in a predator, in phage bacterial system with carrying capacity are damped. So the oscillations are not sustainable. Unlike the standard local Volterra model, they're damped. So when you are saying that you expect cycles in a case where you have the mutual control, you mean that they may or may not happen, or they may be damped.
Yeah. So I would say it's a necessary condition, but it's not a sufficient condition.
Mm-hmm.
Sorry. Maybe, So actually, to connect back to the initial Volterra model is the one that I showed where no one has any self-regulation, right? So that's, by the way, that's a good thing actually for intuitions. Thank you for pointing this out. So this is the original Volterra model, right? There is no self-regulation of either one or two. As soon as you add self-regulation at either of them, then the cycles are damped. The Volterra cycles are killed, and you go to a stable equilibrium, which is another way that self-regulation feels a bit like friction, right? If you had zero friction, you could go around and around forever. As soon as you put friction, you're slowing the motion and you're just going down to an equilibrium. Now, if you put a bit more nonlinearity, you can recover, you can obtain limit cycles. Or if you have three species, you can obtain limit cycles, right? And now you don't have this problem, even with non-zero AII. Thanks. Any other question before I switch to more things like networks, like many species things?
So what is your intuition about the pyramids, the part which you skipped, that you only expect them where you have the bottom-up control, or?
So, yeah, I mean, I would guess that to have very regular pyramids seems very hard to get if you have that the top-down effects are important, because let's say top-down effects should probably create kind of alternating, plus and minus things. You should have one level is very big, therefore the one below is very small, therefore the one below is very big. I don't know if you know this, the green world hypothesis, right? It's this question of, so on land, the world is very green, which means that somehow the herbivores are not depleting the plants very much somehow. And an argument would be that maybe the carnivores are regulating the herbivores very strongly and preventing them from killing all the plants. So it would be more of a hamburger with very small steak, right? Lots of carnivores, very little herbivores, and lots of plants in terms of importance, at least. Maybe not in terms of pure biomass, but at least in terms of something like that, yes. it's a bit more tricky than that, actually. But yeah, okay.
And again, the lore of the phage bacterial people is that, well, they don't usually look at the biomass in a sense of the carbon, carbon-weighted biomass, but in terms of the usual ratios of phages to bacteria, predators outnumber prey by 10 to 1 or 20 to 1.
Yeah.
That's the usual lore, which
Absolutely.
is kind of, there is no absolute reason that it always should be the case, but it seems to be the case.
Yeah, absolutely. And I would say that in the ocean, for instance, the pyramid is generally inverted. So you have very little biomass stock in the phytoplankton, a bit more in the zooplankton, a bit more in fish, and so the reason, oops, perfect. An intuition about this is what's happening there is if the lower levels are very fast, then you're allowing this. This would be the bottom-up explanation. That's you're storing many, almost all of the phytoplankton that is born one day is eaten that day. 90% or something like this of the phytoplankton is eaten the same day that is born. So if you accumulate that over a lifetime, you can sustain a much larger group. But even if you did not have that, you could still have a kind of R-star type of situation where the consumer just has almost depleted the resource, and the one who can survive on very little resource is going to be the one that survives, right? So I don't know. That's why the biomass pyramid it entangles many things, right? Many different dynamics could give the same.
Will you be talking about alternative stable states here, or that is because the alternative stable states, the intuition I have, and I have a paper about it, is that in this phage bacterial ecosystems, phage bacterial resource, so the 3-level systems, the only possibility to have the regime shifts and alternative stable states if the conversion ratio from the nutrient, let's say 1 carbon source, to all the way to phage are different across two paths, right? Imagine you have one phage, 2 bacteria, 1 resource. So they can switch if not always, but as long the necessary condition is that those 2 biomass conversion ratios must be different.
So I can tell you in the Cavertera world, when you have alternate stable states, in fact, it's quite simple. But I don't know the answer to, I don't know how it maps to your situation. Basically, the only way to get alternate stable states here in these 2 species of Cavertera is if you start here with the R tilde that is negative, and your feedback is positive through the other until you kill the other, and then you're alone, and then you decrease, right? So this is the moment where you kill number 2, species 2. And so if you start with a low abundance, then you're trapped here. If you start with a large enough abundance, you grow faster and faster until you kill number 2. And this is exactly being the case where this A tilde tilde is going to be, in this case, negative, I guess. Since this is, let's say, minus A tilde tilde, sorry, 1, 1. A tilde 1, 1, sorry, is positive. And this is minus A 1, 1. So the case in which this is positive, but this is negative, is exactly when you have alternate stable states. How that relates to model parameters, I would need to look at your model. Okay, so in the remaining 20 minutes, 22 minutes, if you're willing to follow me there, we've talked a lot about, so when I was looking a bit at what people were thinking of lecturing about in this lecture, I thought there's something that people will not talk very much about, which is really the complex networks perspective on ecological systems, which is not the thing that I do most of the time. I do disorder, I do randomness, a bit like what Stefano was talking about. But first, the structure of networks of ecological interactions. That's a very important question that many people are discussing. And so I would just want to convey a tiny little piece. Oops. Okay, a tiny little piece of that. I won't go very deep for reasons that you will understand. So I'm skipping my introduction because I gave it yesterday. And so basically, okay, so far we've gone from a single species to maybe predator-prey or consumer resource and non-resource, or maybe a food chain. And then the obvious next step is to go to networks. That's kind of obvious. Now, lots of people have taken this network perspective to think about ecology. And of course, it's also a staple of physics and of applied math. Okay, I look at a complicated system, I'm going to plot it as a network. That's what I do. Now, if you have a network like this, there are 3 different things you could do with them. And I'm going to go to maybe all 3, maybe at least one. The first thing is just describing these networks. If I look at data of networks of ecological interactions, what do they have that is special? That is ecology. What is special about ecology, right? You will not maybe get in other parts of, let's say, in systems biology for gene regulation networks or whatnot. Second question is, why are the ecological interaction networks the way they are? Why do they have the structure that they have? And the third question is understanding the consequences that this structure has for dynamics, for biodiversity, for everything. And what I'm going to say is, as a spoiler, is I have some things to say about 1 and 2, and it's very hard to say something about 3, which is very frustrating, because if you care about ecological networks, usually you would want to know what the structure implies for biodiversity, for coexistence, for dynamics, and that's exactly where we have the fewest results. So I'm going to go quickly through 1 and 2, or at least 1, and there will not be very much to say about 3. So just describing these ecological networks, if I just look at the data, what do I see? Back into this pattern question. Because why do I share this with you? Because every pattern that I mentioned is something intriguing for theory, right? You could say, either I'm going to start from this pattern, I accept this pattern and I put it into my model, and now I see what it gives, or I can try to understand where this pattern comes from. So the problem with a network is too much information. Like, you cannot just look at the matrix of numbers or the adjacency graph of this thing and be like, okay, I understand what's happening. So there are at least a few ways of simplifying this information. One way that is very intuitive for physicists, I would say, is to say somehow all the parts contribute to a collective whole, and we can summarize this whole by some network-wide metrics. Another way that is potentially more intuitive for ecologists is to say, in this network, it's very complicated, but maybe here are mainly carnivores, here are mainly herbivores, here are mainly detritivores. So I can somehow separate this network into big different roles, right? So those are 2 different ways of trying to simplify what the network is about. Finding global structure, collective structure, or finding subsets, subparts that are somehow simpler, substructures that are simpler. So these global metrics, it's a classic complex system question. There are thousands of books you could read. I'm not going to go through them. Maybe you've already heard about all these things. Many things you could measure on a network, which is its clustering, its modularity, shortest path, associative, whatever. It's some global feature of the network. I'll just take one example, which is that thanks to Guy Magrade, who is a member of INTP, who am well, I'll explain what INTP is someday, but let's say my independent organization. So I know this guy, and this is his aunt, and his aunt is a journalist, and she has interviewed Muhammad Ali. So thanks to me and thanks to Gim, you're now at most, 4 steps away from knowing Muhammad Ali, and 5 steps away from knowing George Bush, right? And most complex networks have this property. At least most networks that we see, let's say outside of physics, that are not spatial networks, that are really networks of interactions, tend to have this property of small world, short paths from me to everybody. Why not? So you could think maybe this is an interesting property. I'm going to look at this in my networks. Why not? What's a bit special about ecology here? Well, one of the things is most of the people who actually are plotting networks like this, they're plotting networks of trophic interactions. Typically, this is for predator-prey, maybe for plant-pollinator. You will never see a network like this, or almost never, for competition. And I guess the intuition for that is simple. It's that if you have competition, let's say all of these things are plants, there's no reason why there would be no edge between 2 plants, right? Why would 2 plants not be competing at all? It feels like probably in a competitive system, the network is completely connected, the graph is completely dense, and what you care about is more the value of the coefficients, the Aij. Whereas if you think about who eats who, this is rather sparse, or who pollinates who, this is rather sparse, and so it's maybe interesting to think about just the topology of it, just the structure of who eats who, even if you have no numbers to put on it. Okay, so as soon as you do complex networks, typically you'll see pollination or predation, or maybe infection. Those are the common type of things. Which metrics do ecologists look at the most? that you might want to try to understand theoretically. Typically, nestedness and modularity. Nestedness is something kind of a bit arbitrary. But okay, there's this intuition that if you look at maybe like at graphs, so does anyone not know what adjacency matrix is or how this represents a graph? Can you raise your hand if you don't understand how? Okay, thanks. So the idea is just, this is species I, this is species J, and I put a black thing here if there is a link between I and J. So modularity is the easy one to understand. It's just saying, for instance, species 1 and 2 are interacting strongly together, but they're not interacting so strongly with the others. So there are some blobs in the matrix, right? That's easy to understand. Many networks, ecological networks, are quite modular. Nestedness is something a bit weirder, which says that there are species who interact with a lot of other species, and species who interact with very few other species, right? So maybe you can understand it in terms of generalism versus specialization or these kind of things. Whatever. It's a way of, I mean, you can look at those things.
But nestedness is more than this. It actually means that not all the species we interact with a lot, they are also in the opposite direction. They are interacted with a few and vice versa.
Thank you. So the other thing about nestedness specifically, and that's where it's not obvious that it's true, is that the ones who have few interactions have a subset of the ones who have more interactions. So for instance, you can think of it as, let's say, plant and pollinators. It says that there is a plant who is going to be pollinated by everyone, and there's a plant who is going to be pollinated by a single insect. But the insect who pollinates the rare one is also pollinating the one who is the common. I mean, the insect who pollinates the specialist is also pollinating the generalist, right? It's not like every specialist. So modularity would be a thing a bit more like different plants are specialized on different things. They have, a few plants have a few pollinators, and it's not the same than the next few plants. Nestedness is saying there are plants who are pollinated by everybody, and those who are pollinated by few are pollinated by a subset of those who are pollinated by more of the pollinators. I'm getting tired here, sorry. Anyway.
But to me, nestedness is a hidden one-dimensional variable of both types of organisms, and interactions are dependent on the sum of the variable of organism A plus the organism. As long as A plus B is larger than a threshold, you have an entry.
Thanks. I'll get exactly to that, so thanks. So for now, I just tell you that people can study this. You could study this if you want. Now, what is the point of this, right? The problem is, okay, I could just compare them across networks. I'm going to look at an Arctic food web or a tropical food web. Are they more or less nested and modular? And you'll see many papers doing that. But what does that mean, right? What does it tell me about those networks? It's only meaningful if somehow those metrics, they tell me something about the causes of this pattern or the consequences of this pattern, right? If they're just metrics, I could measure anything, right? It's not obvious that these things tell me something. Before I go into causes and consequences, I'll tell you the other option, which is finding macrostructures. So I have a complex network, but somehow I can cluster it into a few important roles, let's say. Let's say those are all, plants, those are all herbivores, and those are all carnivores, and there are some interactions outside. There are well-established statistical methods to do that. There's a lot of interesting theory behind that if you want. You can look up stochastic block models if that's the kind of thing that you enjoy. It's one of the rightest way to do this. One thing that is a bit subtle, just to give you a hint of why this is not completely trivial, is that sometimes you should group together the species that do not interact with each other, right? If you have a plant pollinator network, then the plants are the things that are not interacting with each other. They're the things that are interacting with the same thing. The insects are not interacting with each other. You define a group by the fact that I am in group A if I interact with group B. And recursively, you can define the groups like this. Okay. So there's interesting theory to be made. I'm just showing you this for your culture, I'm going to skip that. And then a different kind of idea, instead of looking at big groups, is to find axes, like one-dimensional or a few-dimensional axis, which is exactly what Sergey was going towards. So instead of saying that I have a few blocks in my matrix, I'm saying I could just say that for every species, there is some trait, X, and now the interaction probability is a function of Xi and Xj, and the same function for everybody. I'm going to just show you an example here, because I think, yeah, okay. I'm just going to show you this example here. This is a classic model for predation, which is saying, you know what, big things eat small things. Overall, that's a reasonably fair statement. So I'm going to put all my species on a size axis, and each species will have only two traits, two parameters. So actually three, sorry. One is where my species is on this axis. Another one is what is the center of what it eats, and what is the width of what it eats. And so everything that is in this interval will be eaten by that species, right? So now you have 3 parameters per species. You can fit those. And this is an example from data where just computing for every species what would be the best location in this axis, center and width of this thing. The black circles are the empirical observations, and the gray circles is how often you see in a model like this, how able are you to reproduce this just from having those 3 parameters per species. What you see is that roughly just knowing this captures most of the interactions here. So most of the structure that you have in this network is in a hidden way just a function of where I am on this axis, which is basically something like body size. In fact, here we could use the real body sizes, right? Or we could just use this as kind of virtual parameters that we fit. But so this network here, which has this kind of triangle structure, has an underlying unidimensional idea behind it. It could be even, yeah. Okay. So anyway, this has been called intervality, because I'm saying that interactions come just from an interval in along some trait axis. And the thing that's a bit interesting about ecological networks that is not true about many other networks that I know is if you take all the networks that people have in the literature and you try to say, okay, can I just explain them only with this? No, it doesn't work so well with a single axis. But you could say instead of just one axis, I'm going to give myself 2 axes, right? And now I'm going to say instead of just having an interval, it's going to be a box in that 2 trait space. So maybe instead of just one trait, which is body size, let's say big fish eat small fish, but I know that some fish are at the surface and some fish are in the depth. So now I have 2 axes, which is body size and how am I at the depth or in the depth or at the surface. And with 2 axes, I'm just saying all the interactions within the box are going to be observed. And in fact, for most networks, this is how many axes you need to predict very satisfyingly most of the links of a network in many empirical networks as a function of the number of links in a network. So small networks, a single axis is pretty good. Slightly larger networks, 2 axes give you, with this purely interval rule, like this box rule, give you enough. Maybe you need to go to 3. But it's not like you need 1,000 traits to predict who is who. And that goes back to this kind of low-dimensional structure idea that I had before, that once you get into one of these questions, biology is such that probably not all traits are super important at first order. At first order, with 3 traits, you could predict who is eating who.
Does the size algorithm result in the nestedness of the
So actually, it's funny. Nestedness and modularity are triangles, but in directedness are triangles, but in opposite directions. I will not explain that in detail. But nestedness is when you have a matrix that looks like this with zeros, and directedness is when you have a matrix that looks like this with zeros, and it's not the same thing at all. It has very different consequences. But I'll tell you more about this after the lecture if you want. There was another question.
Yes, I missed the one.
What is this?
The meaning of the B panel here.
The B panel is saying, okay, if you wanted to predict all the interactions that you see in the data, how many of those axes would you need to put so that now you say that my condition for an interaction being there is the interaction has the species traits are within this box, right?
What are the symbols?
Each symbol is a different empirical network. And the x-axis is the number of links in that empirical network. And the y-axis is how many dimensions do you need to explain almost completely. You tolerate, a few wrong links, but almost completely, like this, was almost completely explained by just a single axis. Yes. What I'm saying is, I can write it properly. I'm saying that for each species, I'm starting to lack space. Okay, I'm just going to write it here in small, and please have good eyes. Do something about it. So for each species I, I'm going to give myself what is the position of species I in 2 dimensions or 3 dimensions, what is the center of the box for species I, and what is the width of the box for species I in all of these dimensions. And so the idea is that species I will interact with species J if xj vector is in the box defined by Ri minus Wi, Ri plus Wi. This is the only condition. If this is true, then there is a link between I and J. If this is false, there's no link.
So basically, you're saying that if the jth node lies in the same box, then those two will interact.
No, it's more like for each species, I know where its box is, but each species could have a different box. And so your location tells you by who you're going to be eaten. If the position X is, if I am in the box of someone else, I'm going to be eaten by them. And the R, the C, sorry, and W here, yeah, those were C, sorry. The C and W here are just property of the eater that tells me who it is eating.
Basically, if they're in the same box, means they're similar to some degree trait-wise, right?
Yeah.
So why should that mean that you will be eaten by someone who is similar to you trait? Like,
no, actually, so that's the point. That's maybe here it's a bit more obvious. Typically, where you are on this axis and where you eat doesn't need to be in the same place, right? Where you are is this N, where you eat is this C, plus or minus R. So usually you would expect that, in fact, N could be outside of its own box, right? So if you really think that I only eat things smaller than me, then my size would be here, let's say, and my box would be there for smaller fish, right? The big fish is here, but it's eating only smaller fish.
So in the other graphs, so those are the C's or the R's?
Yeah, so this is for so the locations here are the locations of the species, and the box here is the box that belongs to a single species.
Okay, so like let's say the red rectangle.
Yeah.
So it doesn't mean that the species I is within that box, right?
No. So okay, what it means is all the species in that box are eaten by the same species. It doesn't mean that they're eating each other.
Yes, right.
Okay. Yeah, I feel it's a bit of a confusing graph, but you have to blame Anna for it. It's I mean the author of this paper, Anna Clough. It's a very nice paper. I just feel that maybe this graph, this representation is not the most obvious, perhaps. Anyway, so I'll just conclude with, I guess, this more or less. Maybe I'll give myself 2 more minutes. I have 2 minutes still. One thing I wanted to say is, so this is one way of creating the structure, right? I have a simple process that depends only on a few traits, and somehow I create a network that has a plausible structure. And that's a good thing to try to theorize, right? So I can propose a theory, and if it matches my observed network structures, then I'm happy. Now, an interesting thing that people have realized is that many structures that are observed empirically that seem super important could just be kind of accidental consequences of very obvious ways that you could generate a network. So what am I seeing here? What I'm giving this example. I will not go into this graph in detail because it's a mess, and we don't have time. But the idea is very simple. Imagine that the way that you create, see, this is plants and this is pollinators. Imagine that the way that you constructed this network is by saying, I start from a single plant and a single pollinator, and then I have speciation. So now I have 2 plants and 2 pollinators, but there's also only like the offspring has almost the same lengths as the parents. With it loses some, it gains some. If you repeat this process many times, then automatically you get a very nested network, because somehow if you're an offspring of someone who was very generalist, you will be also very generalist, and so you have many rows that are similar. And you can go into the details and see that it creates a lot of nestedness. So it could be that nestedness is not something that is ecologically important at all. It could be just a pure accidental consequence of evolution happening through reproduction and mutation. And it's been called spandrels. The spandrel is a ecology and evolution jargon for properties of a system that are accidental, that are not actually useful from any point of view, from any selective point of view, but are accidental for how the thing evolved or was created, was generated. Okay, yes.
So to create networks and so that we don't run into this problem, should we consider organism, like a single organism within a certain phylogenetic distance? For example, organism 1 and organism 2 should be a certain phylogenetic distance far apart. Would that sort of solve this?
I think so. I never myself played with this model, so I don't know under which conditions you would not have nestedness. But my guess would be something like that. Yes, if the mutations are big enough, like if they change enough things, then you start to lose this spandrel of mutation. Yeah. I will just finish by understanding consequences because I have 2 slides about it, which is basically we don't know. And why don't we know? So we have all these nice network structures that we can see, and we can understand some of them pretty well, where they come from potentially, or we have good hypotheses for where they come from. But what they do to the ecology is very hard to know. And first reason is we don't have the true weights. What we would want in a lot that you love is Aij here, which is the impact of J on the mortality or growth of I. But that is not at all what you measure when you just look outside and you see that this plant is being pollinated. You don't know how much growth it creates. You don't know how much it costs. So you do not have the actual numbers. Yeah. And we also don't know the diagonal elements, right? This self-regulation that I just told you before is super important for many things. Almost no one has measurements of that. We have very big databases of who eats who. You can find them very easily and you can fit them for whatever you want, but no one has big databases of self-regulation. And it's not obvious that even this should be the same number in different contexts. And I guess what I will do at the start of the next lecture is I will explain a bit more about, yeah. Okay, I'll stop here. Thanks.